Okay, Carmen, shall we start?
Yeah, let's go for it. Thank you.
Okay. Okay. Um, thank you everybody for joining today's webinar on quantitative analysis with XRF for mining applications. So my name is Niels Heppe. I'm XRF application specialist here at Rigaku Europe, and today's presenter is Carmen Kaiser-Brückmann. She's as well XRF application specialist here at Rigaku with extensive knowledge as operator in an industrial analytical lab using XRF, and now since over 6 years here at Rigaku in the current role of advising customers on application support and especially mining applications, which we are looking in today. Before we go to the actual webinar, let me please point out that we will answer a few questions after the webinar live here on Zoom. For that questions, please use the Q&A section of Zoom and refrain from putting questions into the chat. For all questions that we can't answer during the webinar, since the time is of course limited, we will come back to you later via email and answer all the questions that will be put into the Q&A section. So thank you very much. And now let me hand over to Carmen. What do you want to present today?
Thank you, Niels, for the introduction, and thank you everyone for joining. Today I would like to share a brief overview of some application examples that I have encountered in the last few working experiences. And so the content of my webinar will focus on very briefly what XRF is, some examples where mining applications are applicable to certain types of spectrometers, because very often we have different types and many people don't understand the differences where they are applicable. And of course, showing you some examples of some of the international norms or mining standards that are basically used in this field. I will show you the applications using different spectrometers, so we will discuss that. And my main goal is to show you the pressed powder method for these applications, because these are usually used in these areas. And so I will discuss the calibrations as well as the preparation and give you some examples of copper ore concentrates, nickel ore concentrates. And lastly, I will follow with a nice example, a little bit different, about MAL, which shows empirical versus fundamental parameter calibrations, followed by a summary, and then we will cover some questions as Niels has explained. So very briefly, what is XRF? X-ray fluorescence is basically an elemental analysis using the fluorescent X-ray. So here you can see, for example, that we have a spectrometer set up with tube and collimators, detectors, and the crystals. So what basically happens is that our sample or our specimen is bombarded with primary X-rays, which give rise to fluorescent X-rays. And these are the X-rays that we will then collimate or focus onto a specific analyzing crystal for WDXRF. And we will get these characteristic K-alpha lines, which we can either measure basically quantitatively with the calibration method, or semi-quantitatively or qualitatively to see the presence of particular elements. So yes, we get two types of spectrometers. One is WDXRF and the other is EDXRF. And both these types of instruments are used in mining applications. I will give you some examples later on, but the two differences are that this is a more compact and robust instrument using a different kind of detector, a much more simple design in terms of hardware. So you can see that here. And really used for suitable for like screening analysis or fast analysis on the field, where the bigger instruments, WDXRFs, a bit more complicated in terms of hardware design, but offers you much better resolution and higher sensitivity, and suitable for very high precision and accurate analysis, also used in mining applications. So yes, as an introduction, very often we use X-ray techniques like X-ray diffraction, X-ray fluorescence, which are ideal tools that can help us to analyze parameters. Like, for example, X-ray diffraction will give you the structure of the minerals, and X-ray fluorescence will give you the elemental composition. So very briefly, in order for us to understand the mineral or the mining side, we need to use these kinds of techniques to understand the quality of our mineral. So the primary resources or raw materials that are used in production facilities, like if you want to make glass or cement or steel or even building materials, we need to do mining in order to get the raw materials. And therefore, these X-ray techniques are very useful. So if I give you some examples of the analytical requirements for mining applications, you can see they can be summarized here. We can do field work, we can do mining. So the geologist really needs to analyze and monitor the grades and blends that are then mined. We also get very important part, which is the on-site laboratory, which is normally operated by chemists or mineralogists to really do proper accurate analysis of the feed and concentrates and also the tailings. And then we also have on-site remote laboratories, which are container laboratories, and where the operators analyze on-site or in very remote areas or even underground mines. And then we, of course, get the automation part and the technology centers where mainly the research occurs. So a geochemistry laboratory usually has many different ways to do chemical analysis, not only elemental analysis, but they also do, for example, isotope analysis. They do mineral composition, and they even take care of the environment. So they need to do environmental analysis or even water analysis to take care of the environment. So very often the geochemistry laboratory and mining together, they drill the cores and they do prospect analysis to draw up the mining plan. In order to draw up the mining plan, it's very crucial because they need to make sure that they have a proper usage of their life of mine. Otherwise, they deplete the good quality mineral, and they need to blend, of course, the various deposits to enhance and make sure the lifespan of the mine is correct. So the mining plan is really there to ensure the best practices are followed when they do mining and to ensure that the mine plan is implemented effectively. And the life of mine really defines the total reserves that are present in that particular area. So like, for example, if you take a limestone quarry, the distribution and quality of the limestone that is used and blended with the waste is really important to extend the life of mine. And most importantly, the mining people need to talk to the quality people to ensure that the factory have their quality aims met in order to make the materials that they are producing. So the mining plan consists of different blocks, and of course this is very important in the mining plan. So different applications can be, for example, the exploration, so looking at the mining side and exploring the deposits, quarry operations, production and mineral processing. We also have oil and gas exploration and industrial minerals, which I briefly spoke about. So if you look, this is an example of a drill core, which is very important to look at the type of mineral that's present and the elements that coexist with the mineral in order to do the ore deposit modeling and mapping correctly for the mining plan. So if we look at the different minerals or the raw materials that can be used, we have different groups, and they consist of like iron and ferroalloys, usually containing a certain amount, a certain group of elements. So now I switch only to XRF. And then we also have non-ferrous metals with a different group of elements. We have the precious metals, which is the PGM, so precious metal group elements. We have the industrial minerals, which are the ones that are usually used for industrial applications, like the cement and the glass manufacturers and the steel manufacturers, also a certain group of elements. And then lastly, we have gas and exploration type, so mineral fuels, with also a certain group of elements. So these groups are very often associated with different international standards. So here we can see, for example, if we have an XRF in the lab, it's really important to abide by the international standards. So here we have ISO and ASTM standards, and they are associated with a certain type of sample. So, for example, if you have iron ore, you need to set up your spectrometer according to these test methods. So all the Rigaku XRF products are norm compliant according to the standard. And XRF is a most commonly used technique for elemental analysis in this case. So these are our examples of our products. So we have Simultex, which is a simultaneous instrument designed for very high throughput with fixed channels. And then we have sequential type WDXRF instruments, which are known as the Primus series. And they also all have different combinations of hardware and geometry. So geometry meaning the relation of the tube to the sample. And then lastly, we also have like a benchtop unit. So in the next few slides, I will show you, for example, some applications related to these products that you see here. These products also come with some application and pre-calibration methods, which are very helpful for the user so that they can use the instrument without setting up their own calibration. So you can see we have a combination of either fused bead methods or even pressed powder methods. So depending on analytical requirements, you can get your instrument with any of these packages as a starting point for your applications. So let's talk a little bit about X-ray fluorescence. It's really used in the mining industry to do grade control because the ore quality really has a lot of variation in it, and it's really important for us to use this as a quality control tool to continually assess the grade of the mineral that we are preparing. So why do we like to use X-ray fluorescence? So we get different kinds of spectrometers. Briefly, I showed you WDXRF, which is the top here. So very often we can get chemical analysis from handheld XRFs, followed by an WDXRF, and then basically followed by a WDXRF to get the more precise work. So why do we have to use all these types of instruments? Because, of course, if you're in the field, you need to understand the material that you want to do the mining. So very often we don't want to take this sample to the lab because it's too much work to prepare the sample and get a very high accurate analysis. So we just use a handheld XRF to give us an idea of the type of mineral, what elements are present. And then we can follow it with an EDXRF to have a high throughput of samples. And then we can take a composite sample and really measure the composite sample for high accuracy and precision. Yeah. So the key advantages of XRF is that, of course, this is a very stable technique, and primarily the sample preparation is relatively easy. We have a wide dynamic range, so we can measure a lot of elements together with different levels of concentration, from basically parts per million to percentage range. And very often we can integrate this in an automation environment to get a lot of samples analyzed at the same time. So very, very useful for geological applications. And mostly XRF is the widely used analytical technique because we have very complicated matrices in minerals and mining applications. So there are a lot of elements, and of course, this is very difficult to deal with if you have other types of analytical tools like atomic absorption or inductively coupled plasma. So this is why we use XRF. So in the next few slides, I will show you some examples of a copper ore and a nickel ore, where we use these different spectrometers, which I briefly explained to you. So simultaneous type, benchtop type, and then a floor standing instrument, where I would like to show you different ways to do a correction. So in our software, we have some correction models, which are very useful for the mining applications. So typical elements in ores that we have, for example, would be if you have an iron matrix, you have other minor oxides and elements present, like shown here, or if you have a copper concentrate or a nickel concentrate, you have another group of minor elements. So why is it important for us to look at the matrix of the material? So yes, the sample could be rich in copper, but the problem is that we have other coexisting elements within that ore body, and of course these coexisting elements will influence each other, and so therefore we need to use matrix corrections in XRF. So here is a nice slide showing you very often the coexisting elements with the different matrix that we have. So as I mentioned, XRF is one of the best methods to measure multiple elements, because you can see we have a large range of elements coexisting with the main ore body, which would be either nickel or copper in the examples that I'm showing. Okay, so in order to do mining applications, mostly we use the press powder method because this is much easier for the laboratory to deal with. But there are some challenges with the press powder method, and I will explain very briefly these challenges. So sample preparation is one of the most important parts of the application. And as you can see in this picture or this diagram, you can see that this material contains various amounts of particles of silica and alumina. And if we do not grind the samples in the correct way, so reduction of particle size, we could influence the intensities. Another factor that plays a role is, of course, pressure. So if we form a pressed powder, of course, the pressure that we use can also influence the intensities. So another point that can influence our application is the infinite thickness, because different groups of elements will be read from different parts of the sample. So we should have an infinitely thick sample. So at the bottom here, we can see also a spectra of calcium, where we show what influence we have on pressed versus loose powder. And you can see if we press the powder into a defined density, then we have much higher intensities, as you can see here. And also the analytical surface should be absolutely perfectly straight and smooth without any imperfections, because very often the lighter elements might be influenced by this. So the fluorescent X-ray that I was talking about will be influenced. So it's really important that preparation is correct. So here you can see if we have large particles, we have a reduced intensity. And if we have finer particles, we have a plateauing out of the intensity. And this is where we want to be. We want to have the finest particle size. Normally, we aim for 45 micron. So yes, very briefly, we have the challenges with the pressed powder method in XRF, because we have matrix and we have mineralogy. And because of this, we have different groups of calcium in these matrices, and therefore we have the challenge of different curves. But if we have the fuse bead method, which is more costly for the mining laboratories, this is not the ideal situation where they want to be. But of course, they can have this as a reference method to check and verify from time to time. So I spoke a little bit about having an infinitely thick sample. So we need to make sure that our pellet is a well-defined density, ensuring that we get a reproducible sample preparation. And most importantly, the pressed powder should be mechanically stable and not breaking in any way. Because, of course, if we subject this to a vacuum, we don't want any loose particles or breaking pellet falling on top of our instrument. Yeah, but if you have a Primus 4, which is tube above, this is actually no problem. So very important is the preparation. So here we can see a nice example of how we receive a sample in a laboratory. So very often we have large and small particles with moisture in between. So it's really important to dry our sample and to reduce the sample in the proper way. So this gives the flow diagram of what needs to happen with the sample, which I will show you in the next few slides. So important is to dry the sample. So very often the moisture sits deep within the capillaries of the sample, and so we need to dry the sample to constant mass. So very often if we have vacuum problems, or we have a long analysis time, extended analysis time, or even variation in our analytical results, it could be something as simple as moisture. So you can see different groups of materials require different types of drying times and drying temperatures to get rid of the moisture that sits deep within the capillaries of the sample. Yeah. Here we have an example of how we need to reduce particle size with what we call a jaw crushing procedure. So we get hard and brittle materials, or we even get soft and elastic materials. So depending on the type of rock, we need to choose the correct reduction procedure. So here you can see the action of a jaw crusher. You can see the particles falling through and the movement of the jaws. Yeah, so the reduction is to have 95% of the particles passing at least 2 millimeters, because you get big particles that would be that need to be reduced. So we get different types of jaw crushers available, bench top ones, bigger ones. So usually samples may need primary jaw crushing followed by secondary jaw crushing, depending on the needs. The next step is to ensure that we do a proper pulverization after the jaw crushing. So initial feed size would be 2 millimeters. This is an example of a puck mill, which is used for pulverization. So the bowl in this case is a chrome steel bowl with a puck inside, and this allows you to have a large volume of sample to reduce particle size further to 212 micron. And then we end up with a good sample here. So very often in the modern laboratory, we have combinations of jaw crushing and pulverization. This is an example of that, with dust extraction now connected to a vacuum, quite useful for eliminating the dust. So after the sample has been jaw crushed and pulverized, it should, of course, undergo the splitting. So here you can see different techniques used for splitting samples. We get random sampling, which gives a very high variation. We get the traditional cone and quartering, which is not always the best either, but it's a little bit better. We get sample dividers or shoot rifflers, which offers less variation. And then, of course, the top end is the sample divider with 10 positions to give you the most superior and the highest degree of splitting the sample accurately. So this really ensures that you get a homogeneous sample. Then, of course, the final sample requires fine milling for XRF, and this can be achieved with any of these instruments that you see here, for example, a seep technique mill or even a mixer mill, to reduce particle size down to what's needed for XRF. Usually, we require less than 45 micron. Of course, we need to be aware of contamination that can occur from our containers. So, of course, if you have different types of vessels, they can cause some contamination, of course. So we need to be aware of this. And here you can see some examples of contamination. So, for example, if you use a zirconia media, then you will have peaks of zirconia and, of course, yttrium. And then, of course, if we use a chrome steel bowl, and you can see, then we contaminate the sample with iron. So these different materials that we use have a certain hardness, and they have a certain amount of abrasion. So we need to be aware of this. Okay, so in order to make the final pressed powder, which you can see here, it's really important that we mix the sample with a binder, and we make the pellet with an aluminium cup so that we have some kind of stabilization. This mixture is usually pressed with either manual or semi-automatic press, or even an automatic press. So here you can see a nice example of pressed powders that are infinitely thick with a flat, smooth analytical surface. And believe me, these are all different samples. They look the same, but this is the aim, to get homogeneity and consistency in XRF. Okay, so once we have prepared the standards, the secondary standards in the correct way, we can then move on to some examples of calibration, which is very important. Yeah. So basically, what is a calibration? In quantitative analysis, it's really important that we have some secondary reference materials to set up a correlation between intensity and concentration. Also important to have the correct range. And we should always remember that our calibration standards should be prepared in exactly the same way as our unknowns. Yeah. So in press powder methods, we have some matrix effects. So we can have absorption effects. So here you can see that in the binary mixture of iron and nickel, with a calibration of nickel, we have some influence. And the influence here is the absorption. So the iron, which you see here, has an absorption edge, which will significantly absorb the nickel with the mass absorption coefficient of nickel here. So, of course, we need to because of this, we need to make a matrix correction. Yeah. Not only do we have absorption, but we also have enhancement effects. So if you have the binary mixture of iron and chrome, and this is the calibration for chrome, we will also see that the chromium is enhanced by the iron. And that is basically shown here with the mass absorption coefficients for chromium and iron. So once again, we need to make a matrix correction. So the calibration curves that we can have in mining applications normally have to be corrected. And here you can see different calibrations where we have the A calibration, where the intensity of the heavy element in the light matrix will be shown. Here we have curve B, where the atomic numbers are very, very close to one another. And then C is where the intensity of the light element in the heavy element matrix. Yeah. So this is the examples. Yeah. So normally we use mathematical corrections to make line overlap corrections, or matrix corrections. Yeah, with theoretical alpha corrections. Yes. But today we will focus on what we call a ratioing method, which means we use an internal standard, either an internal standard method, or we can even use the scattering X-ray correction method. And in this case, I will show you the combination of the Compton scattering together with the theoretical alphas. So these two combinations can help us in the mining applications. So in this example, you can see how we can apply an internal standard correction. So very often if we have the iron ore examples, yeah, so iron ores contain a lot of iron, then of course we can choose an element that's very close by. So usually we need to choose the wavelength of the internal standard very close to the analytical line, which in this case is iron. So we can add a constant amount of this internal standard reagent. So in this case, we chose cobalt because we're not interested in measuring cobalt. And if we mix these combinations, so sample with the internal standard and the binder, and we use hexane as a grinding aid to reduce particle size. And in this way, this mixture is then used to plot the line. So in the application, we measure the iron K beta and the cobalt K alpha. And when we ratio the two, we can have what we call a matrix correction. Yeah, and this matrix correction is called a ratio correction method using the internal standard. Yeah, so it's very, very useful in these applications. And mostly it is also very important to monitor the intensity of the cobalt that's added, because if we monitor this very closely, we can also have an internal check within the laboratory that the grinding process that we are using is very consistent. Yeah. So now I would like to show you how we can combine a scattering FP method for powdered samples. Yeah. So in this way, we use another ratio method. So what is this ratio method? This is where we basically use and measure the Compton scattering line. So this is the rhodium K alpha Compton line, and this will be measured on each and every standard, and it will be ratioed with the intensity of that particular analyte that we want to measure. So in this example, this is the traditional empirical calibration, where we just measured the strontium and correlated with strontium in ppm, but we have a very poor analytical fit. So it needs some kind of matrix corrections. So in this case, our software is able to then measure for each and every standard the Compton line, and this is known as the ratioing method. Yeah, and here you can see intensity of strontium with intensity of the rhodium K alpha Compton. And because we use this matrix correction, we have now improved the regression fit. Of course, because there's a good fit and there's a correction, we get a good accuracy on this method. So usually we try to choose this method only with very heavy elements. So it's applicable to the heavier elements and not light elements. And it's very useful for this. In our software, we have a lot of flexibility because we can also combine the theoretical alpha corrections, which I already explained, which is absorption enhancement corrections, which are with coexisting elements, which are pulled from fundamental parameters, and cannot correct for particle size, in empirical methods. And we combine it with this standard scattering internal standard method. And this compensates basically for the matrix effects, including particle size. But remember, it can only work for the heavier elements most effectively. So in the next few slides, I will show you the differences. So if we take a total ion calibration for iron ore, we get this quadratic fit without any correction. And if we apply the Compton internal standard only, we get a pretty good fit, but still a lot of scatter. But of course, not such a good accuracy. But the moment that we pull in the scattering FP together with the quant method, we can then see that we have a much better fit, and very good matrix corrections are applied to our application with a very, very low accuracy. So very useful for this application. So if we use this Quant Scatter FP method and we try to test, and have a look with the reference values, then you can see here are some certified reference materials, and the ore type, where it's from, yes, or the description of the certified reference material. This is the certified values from the certificate of analysis. And now you can see that we have compared the values from the Quant Scatter FP, which shows a very small deviation from the reference values. Yeah, so very close correlation between the certified values and what we get from the calibration, with a very nice accuracy. But if we just use the normal theoretical alpha correction, we are quite far from that certified value. So not the very best calibration can be achieved with just the matrix correction using theoretical alpha. And if we only use the internal standard method, then also the deviation is much larger. So this concludes and says that the combination of theoretical alpha and Quant Scatter FP is a very useful tool for mining applications. So the last example that I wanted to show you is basically the analysis of copper ore and the concentrates using these spectrometers that you see here. So the first one that we will look at is the Primus 4. The Primus 4 being our best WDXRF floor standing instrument. The applications that I show you will be the pressed powder still. And of course, the copper calibration curves from the instrument showing you differences between the two matrix corrections. So the quantitative scatter FP and only using the internal standard. So you can see quadratic fit always with the very heavy elements, so copper and iron, for example. But immediately you can see the combination of the theoretical alphas with the quant scatter FP improves the accuracy very nicely in comparison with just using the internal standard only. Of course, in the copper concentrates and ore, we also have different elements. So here's some examples of additional elements. So iron and zinc and silver, also using the Quant Scatter FP correction. So you can see a good correlation and accuracy for even the other elements. Of course, the next example is just to show you that even our benchtop instrument, which is the Super Mini 200, also WDXRF, we can also achieve these kinds of methods even on this type of instrument. Of course, accuracy will be different to what it is on the bigger instrument due to the different hardware configuration with different power settings and of course different crystals in comparison to the bigger one. Yeah, but of course also very nice accuracy even with a Quant Scatter FP. So this means all our instruments can have this type of matrix correction. The next example is to show you using a Simultex, some examples of a nickel sulfide ore and the concentrate. So the Simultex 15 is known as our top-end high throughput instrument, which is our simultaneous WDXRF. And of course, here we have some fixed channels. And the fixed channels will be defined by the application that we would like to use. And in this case, the different application here was to have fixed channels for all these elements that you see here. So the range of the methods that we set up on the Simultex for nickel all the way to sodium are shown here using certified reference materials, setting up the calibrations. And these are some of the examples. So once again, showing you that if we only use the internal standard method with a fixed channel for nickel, then of course the quadratic fit is not as nice as it would be by applying the extra combination with Quant Scatter FP. So you can see a much better fit with a very good accuracy in compared to just using internal standard only. Then the copper in this concentrate is also shown, so not a very nice fit here with only the internal standard method, but an extremely good fit once we apply this the quantitative scatter FP correction to the model. Yeah, so very useful matrix corrections. And the last one is showing the iron calibration curve on the Simultex 15, also an improved accuracy and fit on the quadratic curve using the Quant Scatter FP. So the last example that I would like to show you is basically this additional application, which I thought was quite nice and useful to share with you. because this is very visual and very nice to see. So mole is basically used, like, for example, in the cement industry, and we can sometimes mine in a mining quarry. We can get not only high quality limestone, but we can have a combination of a marley limestone and like a marley clay. So depending on where we are mining our material, we may have difficulties in analyzing, for example, this rock. Yeah. So very often, this is a nice example to show you what kind of mole we have. Yeah. So is it a calcium carbonate lime, or is it a clay, a very high percentage of clay that's non-carbonate? So here you can see some very nice examples of one quarry, and on the one quarry we can mine these different rocks, and you can see from the different colors that they are completely different in composition, of course. So this is a pure marl, which is primarily composed of the limestone and the clay. And then, of course, we can get pure clay, so depending on how the color is and the loss on ignition, it can define what kind of sedimentary rock we have in the lab. So the challenge always is, of course, yes, we have very different amounts of silica and alumina and so on, and a lot of different amounts of alloy. So very often in the lab, the different loss on ignitions, the different colors can help us to identify, what type of mineral it is, clay or marl, if you don't have an XRD. Of course, many of the mining laboratories do not have the luxury of having an XRD. Yeah. So then we are stuck in XRF, but we're really not stuck, because we have colors and we have composition and we have spectra. But in our software, we also have the very nice idea that we can not only prepare empirical calibrations, because what did we say? Empirical calibrations need to have matrix matched calibrations. So that means these different materials require different calibrations because of the matrix. So we can go one step further and not only have the Quant Scatter FP, but we can also create our applications as fundamental parameter calibration. And in this way, we have a matrix correction for these different materials. So matrices here can be put together in one calibration curve. So very useful for mining applications. So how does the fundamental parameters calibration works? It pulls in the theoretical intensities and it's calculated for each standard, and it plots together with the measured intensity. So recently I had the pleasure of creating this calibration. So we collected different combinations of the marl, and you can see 16 different types. And these were all certified with the reference method, being fusion. And of course, these calibrations were created with fundamental parameters. And in order to validate the method, we compared the fused bead method with the pressed powder method. And you can see that we get, in most cases, very close results to the fused bead result, meaning that this method, using fundamental parameter with different mole combinations, was very successful. So in conclusion, there are a lot of advantages to the FP method for the calibration, but there are some disadvantages in that we have to know a lot of all the elements that are present. So we need to know at least 100% composition in order to make these methods. Of course, if you need some more information about this, please contact us. So very often people forget about uncertainties of measurement could come from, or where the errors are related to. So very often our analytical errors can be affecting precision and accuracy from different parts. So the first group, which is really the errors that are attributed to the spectrometer, really are from the precision point of view and the trueness. And then the second group are the errors related to sample preparation and the sample itself. And this is very often mostly on the accuracy of the method. So, of course, once we have validated and made sure that our analytical errors are as low as possible, so measurement of uncertainty as low as possible, we can also take part in some proficiency testing. So we should never see this in our lab as a way as a test, but rather just to improve our analytical flow in the lab. Yeah. So proficiency testing very often can take place with different groups. So here you can see that we can even take part. For many years, I've taken part in the GOPT, which is the international proficiency testing scheme that's run by the International Association of Geoanalysts. We used to prepare some samples for this, where I used to work previously, and it's very useful for geological applications, especially for trace elements. So here you can see an example of the type of material that can be tested. And of course, the advantage is that you can benchmark your results internationally with other groups within the same geochemistry applications. You can also take part in Fluxana, but this is usually more for fused bead proficiency testing schemes, and there are many other types. So to end off, I would like to just summarize the webinar and just basically say that, of course, our software modules, which I mostly try to show you today, which are offered on our ZSX guidance software, are very useful for complicated mining applications which have challenges with complicated matrices. And the combination of theoretical alpha and Quant Scatter FP can be very useful for these complicated matrices. So basically, the take-home messages from my side are most importantly is here in Germany, we like to ensure that you have a good and robust and consistent sample preparation to achieve the accuracy that you basically need in your lab. Of course, the calibration is vital, of course. So, of course, you can see you should have a sufficient number of standards. You should have a proper analytical range. And of course, the most important is then to do a continuous assessment of your method. So is your method always fit for purpose? Is it always covering the unknowns that you need to measure? Yeah, and these can be done with a very simple system in our spectrometers called drift corrections. So yeah, those are just some of the pointers that I wanted to show you. And yeah, if we have some time, maybe we could do some questions, if there is. I don't know if there is.
Yes, thank you, Carmen, very much for the excellent insights. And yes, there's a ton of questions in the Q&A section. Sorry for everybody that we can't answer all of them here live, but as promised, we will come back to you via email and answer also your detailed questions. So therefore, I took maybe a bit more general questions from the section. How can we determine the optimum fineness we need in the grinding step?
Oh, yes. So this is always a nice question, because very often in a laboratory we may not have the tools that are needed for this. So of course you have a spectrometer. Yeah. So if you have your XRF, you can of course use this to measure intensities and see how consistent they are. So of course, if you have very coarse particles, you will get a lower intensity. If you have very fine particles, you have the highest intensity. But of course, if you have a particle size analyzer, which mostly some labs do have, then of course this is the best. Of course, it saves a lot of time. Or you could even use the screening method. So if you have different screening sieves, like you can buy them with different sizes, then you could also do it this way.
Awesome. That's also leading to the next question. How much percentage of the sample should pass through the sieve to be considered good?
Yes, this is also a really important question. So normally after our final milling, we should aim that 95% of the particles should pass 45 micron. Then we are satisfied that this is fine enough for us, to use for the XRF, for making the pressed powder. So less than 45 microns, so therefore 95% should pass through 45 micron normally. Yeah. As an initial test, yes.
Okay. So maybe one more question, more to the spectroscopy side, regarding the Compton scattering method. You said we should only use that for heavier elements. What would you define in this case as heavy elements? What is suitable element range?
So this also a very important question. So of course, in the mining applications, we get a lot of heavier elements, and most of them are from titanium onwards. So from titanium to curium, we are more than happy on the spectrometer side to use this matrix correction, which is known as scattering FP. Yes, so normally we use this. Yeah. So if you have silica, for example, you would never use this. So silica, we would rather use a theoretical alpha correction, which would be maybe an absorption or enhancement correction from alumina, for example. So we would not use a scattering line for this type of correction. Yeah.
Do I understand correctly that I can use the Compton scattering for everything that I measure on the lithium fluoride 200 crystal, or are there restrictions?
Exactly, from the LIF 200 or the LIF 220. Correct.
Okay, thank you. I guess we already passed 3 o'clock. I guess we should let us close the webinar here and answer the other questions via email. Thank you again very much, Carmen, for this interesting webinar.
Thank you, everybody. We wish you a nice day.
Yeah, of course. Thank you to everybody who was interested in participating. Thank you so much.